It's been quite a while since we've done one of these Mr. Rainier helps us with our homework videos. So tonight I'm going to see if I can ramp it back up and get going again to help you out a little bit at night with your homework. Today in class we talked about section 4.2. 4.2 covered Rolle's theorem and the mean value theorem. So let's start with a quick review of Rolle's theorem. Now Rolle's theorem, remember, says that if we have any function f that satisfies three very specific conditions. Those conditions being, one, that f is continuous on the closed interval from a to b. Two, that f is differentiable. Now remember, differentiable means it has a derivative. That's what we mean by differentiable. It means the derivative exists. So in essence, when we're checking that, say in the homework problems that we're working on tonight, we have to find the derivative and then we have to show that the derivative exists on the interval that they've given us. That interval is going to be the open interval AB. Remember, continuous, first condition, on the closed interval, and differentiable on the open interval. Because we cannot be differentiable at the endpoints of an open interval. And then finally, the third condition for Rolle's theorem is that f of a, the functional value at a, at our left-hand endpoint, must equal f of b, the functional value at our right-hand endpoint. In essence, the height of the function at a, its y value there, has to be the same as the height of the function at b. So when we draw the function from f of a to f of b, we know that despite going maybe perhaps up initially, we're eventually going to have to come back down, because if we start from f of a and go up, we're going to have to come back down to f of b, because f of b is the same height as f of a. Vice versa, if we go down from f of a, we're going to have to go back up to get to f of b. Now, we could go down and up and any countable number of times between a and b, but we do know that no matter which way we go, be it up from f of a or down from f of a, we're going to have to get back to f of b. So those are our three conditions for Rolle's theorem. And if those three conditions are met, Rolle's theorem says to us that somewhere between a and b, there's a number, c, and at that number, if we find the derivative there and plug in c, we're going to get 0. So the homework starts, problems 1 through 4, begin with us being asked to first show the condition of Rolle's theorem applied to each one of the functions that they provide for us. And then after we show that they apply to the functions that were given on the given interval, then we're supposed to go out and try to find the c, or perhaps more than one, if there happens to be more than one c, for each of those functions in the given interval. So as an example tonight, I've chosen problem number 3. Problem 3 says f of x equals the square root of x minus 1/3 of x. And the interval is the closed interval from 0 to 9. So our first task, remember, is to show that Rolle's theorem does apply to this function. Now to do that, we're going to start just ticking off one by one the three conditions for Rolle's theorem. So remember, condition 1, the function must be continuous on the closed interval from 0 to 9. So our function then is, if you can see this, f of x equals the square root of x minus 1/3. And we have to show that that function is continuous on the interval from 0 to 9. Now, we have plenty of theorems about continuity that we can depend on here. We do not have to use the definition of continuity. So, first and foremost, the first term of this function is the square root of x. What do we know about the graph of the square root of x? Well, if we graph f of x equals the square root of x, we get a function that looks like this. This is the graph of f of x equals the square root of x. And so if we were to ask ourselves, where is that function continuous, we would be able to argue quite successfully that that function is continuous everywhere from 0 to positive infinity. There are no holes, there are no jumps, and there are no vertical asymptotes for that function. So, the square root of x, hey, I got a phone call. I'll be right back.
Call from private caller. Call from private caller.
See, I don't have a phone call anymore. So, the square root of x is continuous on the closed interval starting at 0 and going all the way to positive infinity. From the closed interval from 0 to positive infinity. So we have continuity from 0 to infinity for the square root of x. The other function that we have, the other term of our function, is, we can think about it as just a piece, f of x is equal to negative 1/3 x. Well, the graph of f of x equals negative 1/3 x, that's a line. Has a y-intercept of 0 and a slope of negative 1/3. So that function has a graph that looks like this. F of x equals negative 1/3 x. Again, a function that does not possess any points of discontinuity. And in fact, this time the function's continuous on the whole real line. So we can say there that negative 1/3 x is continuous for all reals. Now, we have theorems that, remember, back in chapter 2 we had lots of conversations about continuity. One of the theorems we had said that the combination of two continuous functions is a continuous function. So in our problem, problem 3, if you look at the function again, our problem is the square root of x minus 1/3 x. We have now shown that both those terms are continuous on intervals much bigger and that include the closed interval from 0 to 9. Consequently, each of those functions must be individually continuous from 0 to 9, and that means that we can use the theorem that says a combination, in this case a difference, of these two continuous functions generates a continuous function. So we have to go through steps such as those to be able to finally state that condition 1 is satisfied. Therefore, f of x equals the square root of x minus 1/3 x is continuous on the closed interval 0 to 9. And now we satisfied the first condition of Rolle's theorem. Now, to address the second condition of Rolle's theorem, we have to talk about differentiability. Prior to talking about differentiability, we have to find the derivative. So we're going to go look for f prime of x. Well, f of x is the square root of x minus 1/3 x. The derivative then, the derivative of that, f prime of x, is going to be 1/2 x to the minus 1/2 minus 1/3. Or if we simplify that, that's going to be 1 divided by 2 root x minus the constant term 1/3. So our derivative, hey, where are you? There you are. Our derivative is 1 over 2 root x minus 1/3. Now remember, our goal here is to show differentiability on the interval 0 to 9, but now the interval is open. Differentiability is always on the open interval. If we look at our derivative, we can see it's clearly not defined at 0. And in fact, it's not defined for any negative value of x as well. However, our open interval from 0 to 9 does not include 0, nor does it include any negative values of x. So, our derivative, f of x equals 1 divided by 2 root x minus the constant 1/3, is defined for all the values in our open interval 0 to 9. So this is defined for all x an element of the open interval 0 to 9. Well, by our definition of differentiability, if that's true, that's what we need. We need just exactly that statement to say that f is differentiable from 0 to 9. So we can now say, therefore, f is differentiable on the open interval 0 to 9. And just like that, we have two conditions of Rolle's theorem satisfied. Now for the third condition. The third condition is usually everyone's favorite condition because there we have to show f of a equals f of b. Or in the case of this problem, we have to show f of 0 equals f of 9. Now, f of 0, remember we're going back to our original function. We're not working with the derivative. We go back to our original function. F of 0 is the square root of 0 minus 1/3 times 0. So f of 0 is the square root of 0 minus 1/3 times 0. Well, the square root of 0 is 0. 1/3 times 0 is 0. So we get 0 minus 0. So f of 0 is 0. Now, we have to show f of 9 equals 0 as well to satisfy Rolle's theorem third condition. So what is f of 9? Well, f of 9 is the square root of 9 minus 1/3 times 9. The square root of 9 is 3. 1/3 times 9, also 3. So 3 minus 3 equals 0, i.e., we've satisfied the third condition. F of 0 equals 0, which happens to equal f of 9. If you hear like noise in the background, there's this weird thing going on. Water is falling out of the sky. I'm not sure what that means, but I'm just going to keep doing this and hope the world is not ending. So there you can see f of 0 equals 0 and f of 9 equals 0. So we have shown f of 0 equals f of 9. So we've shown all three conditions of Rolle's theorem are met. We showed f of x is continuous, we showed f of x is differentiable, and finally we showed f of a equals f of b. So the first part of problem 3 in the homework is taken care of. The job there is to show the three conditions are satisfied. Now our job from that point is to show that somewhere between 0 and 9, there's a point, and there may be more than one, but there's going to be a point where the derivative equals 0. Remember, Rolle's theorem says there's a c between a and b, in our case 0 to 9, so some number between 0 and 9, where the derivative is going to be 0. Maybe it's 2, maybe it's 7, we don't know. It's a point, it's not 12, Mason. Maybe it's a point between, some point between 0 and 9 where the derivative equals 0. So how do we go about doing that? Well, we first find the derivative. We've done that. We know that the derivative f prime of x is 1 over 2 root x minus 1/3. We set that equal to 0. That gets us 1 over 2 root x equals positive 1/3, or 2 root x equals 3. We continue to solve this equation, and we end up with root x equals 3/2, or x, squaring both sides, x equals 9/4. So our derivative equals 0 when x equals 9/4. Well, 9/4 is an element of the open interval 0 to 9. And that's what Rolle's theorem promised we would be able to do. Rolle's theorem promised that somewhere between 0 and 9, we would be able to find a derivative who equals 0. And that derivative turns out to occur at the point x equals 9/4. So those are the steps you're required to follow on problems 1 through 4. Now I'm going to terminate this video, upload it, and I'll film another video here in a few minutes on how to do problems 11 through 14, the problems for the mean value theorem. See you in a few minutes.